Hey everyone, welcome back into our second part. So in our first part we kind of went through the idea of using Bohr diagrams to see how we could draw and combine ionic compounds. And so we're going to continue with that, and just to see what would happen in this case if we were try to combine calcium and fluorine. And so we would have to first draw the Bohr diagrams for them. And so if we drew a Bohr diagram for calcium, followed by a Bohr diagram of fluorine, this would start to look like these. So calcium would have 20 protons and 20 neutrons in its nucleus. Fluorine would have 9 protons, 10 neutrons in its nucleus. Remember that the first shell can only hold 2 electrons, the second shell can hold up to 8, and the third shell can hold up to 8. And then that fourth one brings us up to calcium holding 2, whereas our fluorine atom only goes to the second level. And if we were to count out the number of electrons in the outside shell, we would end up, in this case, just kind of getting 1, 2, 3, 4, 5, 6, and 7. So what we can see through that is that fluorine has this choice to make where it's asking basically, does it want to give away 7 or does it want to pick up the extra 1? Calcium, on the other hand, has 2 in its outer shell. So calcium's looking, okay, do I want to pick up a lot more, in this case like 16 more, or would it rather just give away the 2 that it has? And it's much less work for calcium just to give away those 2 electrons. So calcium, similar to our other one, is going to start to donate these electrons, while fluorine only really wants 1. So this calcium atom would move over to here, and it would donate that 1 electron. This fluorine atom is now stable, and so fluorine is good on the right, but on the left I still have this extra calcium atom. So then we start to say, okay, what can we do to that extra electron? Where can it go? And so the answer to that is to actually just go through and introduce another fluorine atom into the mix. And so if I were to introduce another fluorine atom in, then all of a sudden now I have a whole other spot for this electron to start to travel. And so that electron could go into another fluorine atom, and now calcium can have no more electrons in that outside shell, so it's stable. And fluorine each pick up an extra electron, and so they're stable. And so when I combine them together, what I'm noticing in the end is that really we end up with 1 ion of calcium and 2 ions of fluorine. So our ionic equation, or our ionic compound, ends up being CaF2, where we have 1 atom of calcium for every 2 atoms of fluorine when they combine to balance them out. So we've done a little bit of practice, seen a couple of different examples between the first and second video. So I have a couple of problems here that I would like for you to try out on your own, and use Bohr diagrams to find a balance for the following pairs of elements, and then write the ionic compounds that they would end up making. So I'm going to leave that up to you guys. So pause the video and give it a try, and come back when you're ready. All right, so we're going to move on, and I'll run through the solutions for these. And so hopefully you've had a chance to kind of go through and come up with a combination for them to see what each would need to make it balance out. So we'll start off with lithium and fluorine. So lithium is our third element in our table. Atomic number is 3. And so I always find it helpful if I jot this on the side. It's standard atomic notation. So lithium is 7 and 3. So when I draw a lithium atom, I know I have 3 protons and I have 4 neutrons. So first 2 are in, basically maximizing that first shell. Remember, the first shell can only hold 2, and I only have 1 electron left over. Then if I take a look at fluorine, fluorine has 19 in its atomic mass and 9 for its atomic number. So when I take a look at fluorine, I have 9 protons and 10 neutrons. So first shell can hold 2, second shell If I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And so, as we discussed from before, fluorine wants to take in one extra electron. Basically, as an ion, fluorine would be F minus, because it would be looking to pick up an electron, whereas lithium would be Li plus. It's looking to pick up an electron. So the electron from lithium would jump over and balance the fluorine, and now lithium's balanced because it has a full shell with the 2 on the first one. Fluorine's balanced because it has a full outer shell. And so, just kind of showing that point, I guess, getting rid of this around the outside. So lithium's now balanced with its shell. Fluorine's balanced with its shell. I have one atom of each one. I have Li. The second one, go back and take a look, is beryllium and fluorine. So again, I have a fluorine atom one more time. So, lining our page, we've got beryllium this time. So beryllium is the next one over. It's 9 and 4. And so beryllium would have 4 protons. It would have 5 neutrons, 2 in the first shell. And then after that, it would have an additional 2 on its outside shell, on its valence shell. Fluorine, same thing as the last one, so it has 9 protons, it has 10 neutrons, it has 2 in its first shell, and then after that it has 1, 2, 3, 4, 5, 6, and 7. And so this one electron from beryllium is going to go over and it's going to fill it in, which is great, that's what it needs. But then I have an extra beryllium atom. Well, how do we get around that? It's the same thing that we did from before when we had magnesium, we were working through it. So I'd have to introduce, in this case, introduce another fluorine atom to take up that extra electron. So I'd have another one with 9 protons, 10 neutrons, and it would have its 7 all the way around the outside. And then what we could see from there is that the electron that was left over from beryllium has this extra place to go. And now beryllium is stable, 2 in its outside shell, and each fluorine atom is stable. So what do I have for an equation for this one? Well, I have 1 beryllium atom, and I have 2 fluorine atoms. So BeF2 would be the formula for this. C asks for aluminum and fluorine. So we'll go back in and take a look here for aluminum and fluorine. Just kind of go down our list. So aluminum, in this case, has 27 for its atomic mass and 13 in its atomic number. And so we have 13 protons, we have 14 neutrons, 13 protons, 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So 13 protons matches up with our 13 electrons going around its outside shell. Fluorine now, we've done this a couple of times, so I've got 9 protons, I've got 10 neutrons, the first 2, and then after that it fills its shells, 1, 2, 3, and 4, 5, and 6, and 7. And so hopefully by now what we're starting to see here is that I can take an electron over and fill it up, and what that indicates is that I actually end up needing a couple extra of my fluorine atoms. So I'm just going to copy a couple extra over to show what we would need to make this thing balance out. So if I had 2 more fluorine atoms here, then I can see I'll have 1 electron for aluminum filling the first one, my second electron in aluminum goes down and fills the second one, and then my third electron can go over and it can balance out the third one. And so now aluminum's balanced, it has 8 in its outermost shell, because remember, once those electrons are gone, really this orbit isn't really here. the orbits around the outside shell of these Bohr diagrams really don't exist. They're more like pathways, kind of like how the planets go around the sun. Okay, it's a kind of a line that we assume that these electrons are contained in, but they're not physical lines. They're just kind of these imaginary pathways that we can assume similar to how planets would travel around the sun. So aluminum now is stable. Each of the fluorine atoms are stable, and so what I'm finding out here is that I have one aluminum atom and I have 3 fluorine atoms, so it's completely balanced out. Going on to D. D is magnesium and nitrogen, so let's take a look at that one and see what that looks like. Okay, so D, magnesium, looks like it has an atomic mass of 24, and it has an atomic number of 12. So magnesium is going to have 12 protons and 12 neutrons. It's going to have 2 in its first shell. Remember that first shell's max is 2. Second shell's max is 8. That's going to bring us up to 10 in total. And then it's going to have 2 extra ones on the outside to make 12. Nitrogen, on the other hand, nitrogen has an atomic mass of 14, it has an atomic number of 7, and so when I draw nitrogen out, I'll have 7 protons and 7 neutrons. 2 in that first shell mean that the second one can only have 5 left. So 1, 2, 3, 4, and 5. So now I'm going to do the exact same process again. What I'm noticing now is that I have 1 electron from magnesium that's going to go over, and it's going to fill 1 spot. I have another electron from magnesium that's going to go over, and it's going to fill 1 spot. Well, I still have an extra spot left over for nitrogen. So what does that tell me? Well, in most cases what we've been doing is adding an extra 1 on the right to make it so the ones on the left can get rid of their electrons. But in this case, the ones on the left that are donating electrons, I'm out of them, and nitrogen still needs 1 more. So I actually need to add in another magnesium in this case. So we're going to go through and we're going to add in another magnesium. Okay, now if I add in another magnesium, hopefully you can kind of look ahead and see now I'm going to donate 3 electrons to that nitrogen. I'm going to end up with an extra magnesium left over. So in this case, I'm going to end up with needing another nitrogen afterwards. So I'm going to copy that for right now, and then we'll see how that kind of comes into play here in a second. So let's start to move some of these over. So I'm going to take this electron, it's going to go over and fill here. I'm going to take this electron, we're going to make it go over and fill right here. And then I've got this electron that's going to come all the way over, and it's going to fill the nitrogen for that one. Now I have an extra electron that's here. This electron is going to go in, it's going to fill here, but now this other nitrogen still needs 2 more electrons. So what does that tell me? It tells me that I'm going to need an extra magnesium. So let's copy 1 more magnesium in. And then when I copy that last magnesium in, what I can see is that finally this thing balances out, right? Electron goes here and balances, electron goes here and balances, and nitrogen itself now is completely empty in both of them, and my magnesium is completely emptied down to the second energy level where it's full, so it's stable, and actually looks like neon. So everything's stable. The electrons are where they need to be to maximize each ring. And if I count my overall atoms now, I ended up with 3 magnesiums to balance out 2 nitrogens. And so Mg3N2 would be the formula that would work for magnesium and nitrogen. Okay, let's take a look at the last one. The last one is aluminum and oxygen in part E. So aluminum and oxygen. So if I take a look here, aluminum was one that we did earlier, 27 and 13. And so aluminum has 13 protons and 14 neutrons, has 2 in that first shell. Second shell can hold 10. And then after that I can have 3 more. 1, 2, and 3. Oxygen, 16 and 8. 16 for its atomic mass, 8 for its atomic number. Oxygen has 8 protons and 8 neutrons, so 1 and 2 in that first shell. And then 1, 2, 3, 4, 5, and 6. And then 2 more in the middle, give me my 8. So, oxygen wants to take in 2 electrons. Aluminum has 3 to give away. And we hopefully here, based on the last example, we can start to see what's going to happen. So, aluminum is going to start donating its oxygens, same way it did before. But now, oxygen's full after aluminum only donated 2. So, I'm going to have to introduce another oxygen into our problem here. So I have another spot for the extra aluminum to go. So, we'll add in an extra oxygen. And now what can start to happen is that this other aluminum has a place to go. But now, oxygen still needs 1 more, and I'm out of the aluminums that I had. So from our previous example, we know we have to add more of this one. So we're going to add another aluminum in. And if I add another aluminum, now I can start donating electrons again. So I've got extra electrons here to donate. 1 and 2. Oh, sorry, my bad. 1. And then, oh, I did it again. So 1 right here. Sorry about that. And then now oxygen is full on that Bohr diagram, that shell. I've got 2 extra electrons left over for aluminum. So how do I get around that? Well, I have to introduce another oxygen atom. So if I introduce another oxygen, now what I can see is that I have 1 electron that's here, and I have another electron that's here, and my aluminums, the electrons are all gone. The oxygens, they're completely filled now. They have 8 in that outer shell, which is what I'm looking for. And so I would say that this would be Al2, because it took me 2 aluminums, and it took me 3 oxygens to get there. So Al2O3 would be my balanced equation that would make my ionic compound for this. So, drawing Bohr diagrams is obviously kind of a tricky way to go through every time. It's quite tedious. It takes a while. So obviously there's got to be a simpler way to go through this. And that's what we'll talk about in our last video on going through ionic compounds. So we'll continue on when you click on video 3.